Hello, everyone. In this video, we will discuss derivatives of inverse hyperbolic functions. Derivatives of inverse hyperbolic functions. These are the differentiation rules for inverse hyperbolic functions. Which are valid whenever x is in the domain of the inverse hyperbolic function. Even if the inverse hyperbolic tangent and inverse hyperbolic cotangent may have the same derivatives, each is valid for a specific interval, which is also the domain of the inverse hyperbolic function. Let us review the logarithm definitions of inverse hyperbolic functions. And the following reciprocal arguments identities. Derivation of the derivative of the inverse hyperbolic sine function. Let y equals the inverse hyperbolic sine of x, which means that the hyperbolic sine of y is equal to x. Take the derivative with respect to x of each side of the equation. The derivative of the hyperbolic sine of y is hyperbolic cosine of y. However, because y is a function of x and we need its derivative with respect to x, multiply the result by the derivative of y with respect to x. This differentiation process is called the chain rule, and it is applied in differentiating composite functions. Use a hyperbolic identity to express hyperbolic cosine of y in terms of hyperbolic sine of y. Afterwards, express the equation in terms of x. Substitute x equals the hyperbolic sine of y. Divide both sides of the equation by the square root of quantity x squared plus 1. Therefore, the derivative with respect to x of the inverse hyperbolic sine of x is equal to 1 all over the square root of quantity x squared plus 1. Derivation of the derivative of the inverse hyperbolic tangent function. Let y equals the inverse hyperbolic tangent of x, which means that the hyperbolic tangent of y is equal to x. Take the derivative with respect to x of each side of the equation. Apply the chain rule as in the previous derivation. The derivative of the hyperbolic tangent of y is the square of hyperbolic secant of y. Use a hyperbolic identity to express hyperbolic secant of y in terms of hyperbolic tangent of y. Afterwards, express the equation in terms of x. Substitute x equals the hyperbolic tangent of y. Divide both sides of the equation by the quantity 1 minus x squared. Therefore, the derivative with respect to x of the inverse hyperbolic tangent of x is equal to 1 all over the quantity 1 minus x squared. Derivation of the derivative of the inverse hyperbolic cosecant function. Let y equals the inverse hyperbolic cosecant of x, which means that the hyperbolic cosecant of y is equal to x. Take the derivative with respect to x of each side of the equation. Apply the chain rule as in the previous derivation. The derivative of the hyperbolic cosecant of y is the negative of hyperbolic cosecant of y times the hyperbolic cotangent of y. Use a hyperbolic identity to express hyperbolic cotangent of y in terms of hyperbolic cosecant of y. Afterwards, express the equation in terms of x. Substitute x equals the hyperbolic cosecant of y. Divide both sides of the equation by the square root of quantity 1 plus x squared. Therefore, the derivative with respect to x of the inverse hyperbolic cosecant of x is equal to the negative of 1 all over the product of the absolute value of x and the square root of quantity 1 plus x squared. Examples. Find the derivative. Number 1. Y equals the inverse hyperbolic cosine of t plus the inverse hyperbolic sine of t. Solution. dy dt is the derivative of y with respect to t. Differentiate using inverse hyperbolic function rules. Hence, dy dt equals 1 over the square root of quantity t squared minus 1 plus 1 over the square root of t squared plus 1. Number 2. W equals the inverse hyperbolic cosine of 1 over z. Solution. The function does not fit exactly into a basic inverse hyperbolic function rule. However, we can rewrite it using a reciprocal identity. W becomes the inverse hyperbolic secant of z. dw dz is the derivative of w with respect to z. Differentiate using an inverse hyperbolic function rule. Thus, dw dz equals the negative of 1 all over the product of z and the square root of quantity 1 minus z squared. Number 3. F of x equals 2 times the inverse hyperbolic tangent of x times the inverse cotangent of x. Solution. F prime of x is the derivative of f with respect to x. Apply the constant multiple rule and the product rule. Differentiate using an inverse trigonometric and an inverse hyperbolic function rule. Simplify the derivative. Combine the rational expressions using the LCD method. Therefore, f prime of x equals 2 times the quantity of 1 plus x squared times the inverse cotangent of x minus 2 times the quantity 1 minus x squared times the inverse hyperbolic tangent of x all over the quantity 1 minus x raised to 4. Number 4. F of x equals 1 over the inverse hyperbolic sine of x. Solution. F prime of x is the derivative of f with respect to x. Apply the quotient rule. and differentiate using a basic differentiation rule and an inverse hyperbolic function rule. Simplify the derivative. Therefore, f prime of x equals the negative of 1 all over the product of the square of inverse hyperbolic sine of x and the square root of quantity x squared plus 1. Number 5. H of t equals the inverse hyperbolic secant of t all over the natural logarithm of t. Solution. H prime of t equals the derivative of h with respect to t. Apply the quotient rule. Then differentiate using a logarithmic function and an inverse hyperbolic function rule. Next, simplify the derivative. Combine these expressions in the numerator using the LCD method. And apply a property of fractions. Thus, h prime of t equals the negative of quantity of natural logarithm of t plus the square root of quantity 1 minus t squared times the inverse hyperbolic secant of t all over the product of t, the square root of quantity 1 minus t squared, and the square of the natural logarithm of t. Number 6. Y equals 4 times the inverse hyperbolic sine of x times the inverse sine of x. Solution. dy dt is the derivative of y with respect to t. Apply the constant multiple rule and the product rule. Differentiate using an inverse hyperbolic and an inverse trigonometric function rule. Afterwards, simplify the derivative. Combine these expressions using the LCD method. And rewrite this factor in the numerator, as well as this factor in the denominator. Thus, dy dx equals 4 times the square root of quantity 1 minus x squared times the inverse sine of x plus 4 times the square root of quantity 1 plus x squared times the inverse hyperbolic sine of x all over the square root of quantity 1 minus x raised to 4. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.